So for today's video, we're going to be doing something a little bit different. I'm going to actually be explaining what time complexity is because I realized I haven't quite made that clear in my other videos. Now, if you take a university course and go through time complexity and runtime notation, you'll know that it's a really large subject that can't really be put into an 8-minute video. So I'll just try to do a condensed version that focuses on the bits that I think are important in the context of technical interviews. So let's get started off with time complexity. Basically what it is, let's say like you're given an array. We have like a whole ton of like random numbers here, right? You have to be able to grab those values in some way in order to solve a solution or manipulate it in some way. Let's say like you want to have a method like add that basically goes over every single element, sums it all together, and returns that value, right? In order for that to happen, the add method needs to be able to access every single element within that array. In doing so, there's a little bit of processing time that needs to be done in order to retrieve and get those values, and that's where time complexity comes in. So a common way of describing this would be having writing it as O of n. Also, to kind of explain big O in more detail, basically big O represents the upper bound of a runtime function, whereas there's other ones that exist like omega, which describes the lower bound, theta, which describes the exact bound of the complexity, and little o, which describes the upper bound excluding the exact bound. For the purposes of technical interviews and other things like this, we generally want to focus on big O, but in case you want to take a look more into that, they do exist out there. Now, to break down what O of n is, pretty much n represents the number of elements in the actual array itself. Let's say you needed to loop through, sum up all the values, and then also multiply all the values, and then return those values together. So let's say we have a sum and multiply method that what it does is basically loop through and then sum all the values, and then we loop through it again, and then we multiply all the values. In this case, we're not actually just accessing each element once, we're accessing every single element twice. In this situation, the time complexity of this would be O of n plus n. N plus n can just be kind of reduced down to O of 2n. That's another way of writing it. And that's what the time complexity of this one would be, because let's say you want to add multiple elements to this array. So we have 6, 7, 8, 9, so on and so forth. The more elements you add onto it, the longer it's going to take. So time complexity is just kind of a way of saying when you add when you add a whole ton of elements to the array, how efficient would it be under those circumstances, pretty much. That's why people would use time complexity. So in this case, for this sum and multiply method, you know that the time complexity over 2n means that it'll have to loop through every single element in the dataset twice. It's generally considered that if you loop through it, let's say 2 times, or loop through it even 7 times, right? Let's say a method is O of 7n, you have 7 for loops that loop through every single element. It's still a negligible amount, because you really even though you're looping through it 7 times, it's still the computer is still able to handle that with relative ease. Even if you increase the dataset by a large amount, the computer is still generally able to handle that. Where it does begin to struggle though is if you have a scenario like this. So let's say a method like toSum, right? You have a toSum method. With this method, you if you had to loop through it twice, so for every single element in the array, you have to loop through every single element again. So for 5, you want to do something with 6, do something with 7, do something with 12, do something with 6. With the next value, you move forward, and you want to do it again. You want to do something with 5, do something with 6, do something with 7, do something with 12, do something with 6. You notice that at the very end of this data set, you notice there's 5. You go 1, 2, 3, 4, 5. You'll notice you'll have to loop through it 25 times, right? So n will have to be done 25 times, and which is basically just if you notice, it's n squared. Because for every single element, you're going to have to do it over and over and over again. You can kind of begin to see how this might be considered inefficient, because let's say you add a 6th element. All of a sudden, it doesn't happen 25 times, it happens 36 times. and with 749, so on and so forth. If you have a really, really large data set and you need to loop through it twice, that's where the computer begins to struggle because you're kind of wasting the memory here. And this is why people tend to look for O of n solutions, or like solutions that aren't squared, in order to make their algorithms more efficient. So it's all just a matter of accessing the like the elements within the array, basically like making that as a few amount as possible, along with having n and n squared. So we have, right now we have O of n, and then we have O of n squared. There's also something called log n. O of log n is used for like searching algorithms like binary search and things similar to that. So let's say like you have like numbers like 2, 6, 4, 5, 8, and you want to perform a binary search with it, which is pretty much just having the number of elements you need to search for each time, having it again. Basically, every single time you iterate through, the amount of elements you have to search decreases by half each time. So if you imagine that on a graph, like the amount of power you would have to use goes down every single time because you're having all of the elements at at every single given iteration. So that's another thing you're looking for. Generally, log n is better than n because you're having it about each time. So this one is better, well, or like less than the time it takes to do an O of n solution, which is less than an O of n squared solution. Now, there's also other ones like other algorithms which can be exponential as well, something to the power of n, and there's like things like you can combine different parts of it together. So like we have like let's imagine we have a O log n algorithm, and within that O log n algorithm, you also have to do something that would be that would necessitate an O of n algorithm as well. That would be an O of log n plus an O of n log n algorithm, which would then reduce down to O of n log n. You'll notice that there's a lot of O log n algorithms for sorting because that's currently what we have so far. That's the best possible like sorting time complexity that we have currently. There's things like that, and yeah. So generally, when you're creating algorithms, you want to make sure that it's the smallest amounts possible in terms of the time complexity. Also, another time complexity exists called O of 1, which pretty much doesn't access the data set at all. That's something to keep a note of. Okay, generally when you're doing when you're creating algorithms, you want to look for the lowest time complexity possible, and you can kind of ignore situations where it would be O of 2n, or you can mention it because O of 2n can be roughly reduced down to O of n since they're so close together in time complexity. But generally, it's like enough to not really have to go into deeper context with. Generally, you want to be looking for like the really big changes where it's like O of log n, O of n squared, etc. Hopefully that clears things up a little bit.